So today we're going to be doing section 11.6, which is finding the area of regular polygons. And this can be found on page 762 in your textbook. If you have not already outlined this section, you need to go ahead and pause this video and outline the section before you continue on. In section 11.5, we learned how to find the areas of circles. And we learned that to find the area of a circle, it was just going to be pi r squared. And we also learned how to find the area of a sector or portion of a circle. So now we're going to find the area of regular polygons inscribed in a circle. But what is a regular polygon? What was our definition? Well, a regular polygon is a polygon that's both equilateral and equiangular. So that means that it has all sides congruent and all angles congruent. Here I have the key vocabulary for this particular section, which is center of a polygon, radius of a polygon, apothem of a polygon, and central angle of a polygon. You need to make sure that you have these definitions either from the textbook or the definitions I have here on the screen in your notes, okay? So the center and radius of a polygon are the same as the center and radius of its circumscribed circle. So point P is going to be the center of my circle, but it's also going to be the center of my inscribed polygon, which in this case has 6 sides, so it is a hexagon. And PM and PN are both going to be radii of my polygons. They go from the center to a point on the circle, so they're radii of circle P. But they also go from the center to a vertex of the polygon, so they are a radius of the polygon. The distance from the center to any side of the polygon is called the apothem of the polygon. So P is the center of the circle and the center of my polygon. And if I go from P to Q, this segment is called the apothem. And it is always going to reach the side, intersect with the side, at a right angle. So the last vocabulary word I have is the central angle of a polygon. And it's going to be the angle formed by 2 radii to consecutive vertices of the polygon. So in my figure, I have point M and point N are consecutive vertices. So therefore the angle MPN is going to be a central angle. And I can find the measure of each central angle by taking 360 degrees, which is the measure of the entire circle, and dividing by the number of sides n. If I was solving for this particular hexagon, my n would be 6 sides, so it would be 360 degrees divided by n. So here I have triangle AOB, and it's an isosceles triangle. So if the congruent legs of the isosceles triangle are radii, so OA, OB, they're congruent because we know that all the radii in a circle are congruent, then the apothem is the height to the base. So AB is my base, and my apothem is my height. And so the apothem is always going to bisect this central angle. It's always going to take that central angle AOB and split it in half. So let's look at an example problem. In the diagram, ABCDE is a regular pentagon inscribed in circle F. Find each angle measure. So the first measure it asks me to find is the measure of angle AFB. So angle AFB is going to be a central angle of this polygon. It goes from two consecutive vertices. And I know that the formula to find the measure of a central angle is going to be 360 degrees divided by n. And I know that my number of sides is 5 because a pentagon has 5 sides. So to find the measure of that angle, I'd simply take 360 degrees and divide by 5, and that gives me 72 degrees. The next angle it has me look for is the measure of angle AFG. So AFG. Well, I know that FG is the apothem of this triangle. It goes from the center, point F, to G, a point on the side. And I know that the apothem bisects the angle. So this angle, measure of angle AFG, is simply going to be 1/2 the angle I found in part A. So if I take my original 72 degrees and divide by 2, I find that the measure of this angle is 36 degrees. Last, the problem asks me to find the measure of angle GAF. That's this last remaining angle right here. But I know that AFG forms a triangle, and I know that the angles in a triangle always add up to 180 degrees. So the measure of angle AFG, which I found in part B, plus the 90-degree angle, plus the measure of GAF are going to be equal to 180 degrees. I solve for my unknown, and I find that the angle GAF, the measure of the angle, is equal to 54 degrees. So let's do 2 more practice problems to find the measure of the central angle given the number of sides. And notice that the instructions tell me to round answers to the nearest tenth of a degree if necessary. So in number 2, I'm told that this regular polygon has 36 sides. So I know that n equals 36. And I know that I can find the central angle by taking 360 degrees, the full measure of a circle, and dividing by n. Substitute in my value for n, and I get 360 degrees divided by 36. This divides really nicely, and I'm left with just 10 degrees. And I didn't need to round my answer to the nearest tenth of a degree because I already had a whole number answer. In number 3, I'm told that I have a regular polygon with 120 sides. So again, n is just equal to your number of sides, so it's 120. Same formula as before, 360 degrees, divide by n, substitute in my value for n, 360 degrees divided by 120. And again, this divides really nicely, and I'm left with 3 degrees. So again, I did not need to round because I had a whole number answer. So now you're going to find the measure of a central angle for yourself. And you're going to do the shape that's designated for your class period. So if you are in second period, you need to find the central angle of an 11-gon. If you're in third period, you need to find the central angle of a nonagon. If you're in sixth period, you need to find the central angle of a 15-gon. And if you're in seventh period, you need to find the central angle of a decagon. And remember again that you are rounding your answers to the nearest tenth of a degree if necessary. So how does this help us find the area of an n-gon. So you can find the area of any regular n-gon by dividing it into congruent triangles. So once again, I have a hexagon here on the board, and I can divide this hexagon into 6 equal triangles. So if I find the area of one triangle and multiply it by the number of triangles, then I have my total area. And remember that the area of a triangle is going to be 1/2 base times height. Well, the base of my triangle is going to be S, and the height of my triangle is going to be the length of the apothem. So I start with the equation 1/2 S times A times N, the number of triangles. And the commutative and associative properties of equality tell me that I can rewrite the equation as 1/2 times the apothem times N times the length S. Well, I know if there are n congruent sides of length S, then I simply have the perimeter of my polygon. P is the number of sides times the length of the side. So I can also find the area by taking 1/2 the apothem and multiplying by the perimeter of the polygon. And that's where this theorem for the area of a regular polygon comes from. So the area of a regular n-gon with side length S is half the product of the apothem A and the perimeter P. Or if you don't know the perimeter, you can also do 1/2 the apothem times the number of sides times a singular side length. So what would be the area of a hexagon with side length 6 centimeters? Well, once again, I know that I can divide my hexagon into 6 equal triangles, and I need to find the area of a singular triangle. So here I have my singular triangle. Okay? And I know that my side length is 6 centimeters. And I know that my apothem bisects this side. So to find this length apothem, what do I need to know? Well, to find a side length, if I have one side length, I either need an angle, so I could use trig, or I need the hypotenuse, so I can use Pythagorean theorem. Well, I don't know what the hypotenuse is, but can I find the measure of this angle? Absolutely. So I know that the whole angle is going to be a central angle. So the measure of the angle is going to be 360 degrees divided by my number of sides. I have a hexagon, so I have 6 sides. So it's going to be 60 degrees. And I also know that the apothem bisects this angle. So it's going to be 30 degrees for just this portion. Since it's a triangle, I know that this side's 60 degrees. So now I could use trig, or I could use my special right triangles to determine the length of the other side. So I know that if this length is 3 centimeters, then my apothem is 3√3 centimeters. Okay? So I know that my side length is 6 centimeters. it gave that to me in the problem. And I know that my apothem is 3√3 centimeters. And if I have one side as 6 centimeters, I know that the perimeter is going to be 6 centimeters times the number of sides, which is 6, so 36 centimeters. So I know that the area of this hexagon is going to be 1/2 times 3√3 centimeters times 36 centimeters. Okay. Which is equal to 54√3 centimeters squared. Do not forget your units. I am looking for an area, so my units will be square units. And then if I wanted to approximate this area, it would be approximately 93.53 centimeters squared. Okay. So once again, if I'm finding lengths in a regular n-gon, if I have a regular n-gon with a radius r, I may need to first find the apothem or side length s, so apothem A or side length s, to be able to actually find the area. And then I have 3 different methods I can use. I can use the Pythagorean theorem, so 1/2 s squared plus a squared equals r squared. If I have 2 of the 3 measures, r and a or r and s. I can use special right triangles. So if I have any one measure of r, a, or s and the value of n is 3, 4, or 6, so they're letting you know it's only going to work if it's a triangle, a quadrilateral, or a hexagon. And my third option is to use trigonometry. And that's if I have any one measure, r or a or s, because I can always find the measure of that central angle, and I can always find the measure of 1/2 the central angle. So if you need to, go back and look at the example problem for a hexagon, because you're going to find the area of the regular polygon assigned to your period, given that the side length is 6 centimeters. So your S is equal to 6 centimeters. So second period, you're once again going to be finding the area for an 11-gon. Third period, you will be using a nonagon. Sixth period, you will be using a 15-gon. And seventh period, you will be using a decagon. Please make sure that you bring these notes and your answers for the practice problems to class on Monday so that we can go over them. Hope you had a great weekend.